This is lecture 5, chapter 3. So we finished chapter 2. We talked about 2D and 3D equilibrium, and we just mainly worked on finding vectors and putting vectors together from forces and unit vectors. So now we're going to take this one step further, and we're going to look at what are called equivalent systems of forces. But mainly this chapter deals with moments. And so first, let's start with the basics, and hopefully you've had a chance to review the material. I would recommend looking over this section in the book before you watch the video. Just you'll familiarize yourself with some of the figures I'm going to be showing. So we want to first distinguish between external and internal forces. So an external force is something that you apply to a rigid body. So in this example, you have people trying to pull this truck. And also the forces that are on the truck include the reaction forces at the wheels and also the pull of gravity and due to the center of mass, and also, the forces being pulled by the people, which is equivalent to F. Now, internal forces, these are not chemical or atomic forces. What we're really talking about in this course when we talk about internal forces are things that would be confined to the truck itself. So the truck, it has a wheel, has an axle, has a motor that's sitting on a motor mount. And so all those forces that are pushing back on one another are all internal. So they don't affect the overall forces that are required to move the truck or its static condition as it sits. So within forces or vectors, we have the idea of the principle of transmissibility. And this just simply says that if you apply a force at a point, you can consider it active along the entire line in its direction. So these two forces, F and F prime, are equivalent. It doesn't really matter. And so this comes in handy in some of the problems where you want to have the force in a different place as far as do it for calculation purposes. It also helps when we're talking about moments, because when we're looking for right angles relative to the force, which will be explained later in this. So the idea of transmissibility also comes in with the push or pull. So whether you're pushing or pulling the truck, it doesn't matter, it's still the same vector. And so you see the vectors applied at the same location on the bumper. And so whether you're pushing it from behind or pulling it from the front, it's the same. Now, this is good in our world of rigid bodies with an infinite modulus, but it's not true in the real world where, depending on where you apply the force, even if it's within the line of transmissibility, you still have different reactions based on the materials. But that's not something we need to worry about. So a little basic vectors. I'm sure you've seen this, but recall that if you cross P cross Q, you get vector V, which is then perpendicular to the plane in which P and Q reside. The angle between P and Q, theta, then relates to the magnitude of that P cross Q by V being the scalar value equals the scalar value of P times the scalar value of Q times the sine of theta. And turns out that the magnitude of V is actually equal to the area of the parallelogram that P and Q form. But that's not something we're going to deal with in this course. It's just more of an interesting math fact. Now, in terms of directions, you can imagine that depending on whether you do P cross Q or Q cross P, that is going to change the relative direction of V. And so we follow the right-hand rule. And the easiest way is, as the picture indicates, take your hand, and if you imagine your fingers as P and your palm as Q, as you rotate your fingers into your palm, then your thumb points up, which is where V would be. If you do the opposite with your hand and you hold your hand upside down and you curve Q into your palm in the other direction where Q is coming to P, where your fingers are coming to P, then your thumb is going to point down. And so this is the sign convention that we'll use throughout the quarter. Oh, before I get to that point, I would like to mention is how do we find the actual cross products? This is something that you should know, but I wanted to quickly review it. So let's look at our graph. All right, so here's our paper. So here we have V equals P cross Q, V magnitude, P, Q, sine theta. Now, when I draw vectors, I always put a hat on them. That's how you know the difference between scalars and vectors. On PowerPoint, vectors are bold, and these are italics. So how do we cross vectors? So first off, we want to put them in their components. So we know that P equals Px plus Py ij plus Pzk, and Q equals Qxi plus Qyj plus Qzk. So if we take the components and we set them up as V, then this is how you'll draw it when you're doing your homework. You have your I, J, K above, and then you just simply put in your Px, Py, Pz, Qx, Qy, Qz, and these would just simply be the values of those respective components. And remembering that if we want to cross for I, cover I, and we know it's Py times Qz, Py times Qz minus Pz times Qy. And that is our I component. So for our J component, we say, now you may have learned in high school plus minus plus, where you put a minus here. That works fine too. Another way to do it is to just say plus this, but reverse the order here. That's how I learned it. So I'm putting a plus there, but now I'm saying Pz times Qx. This is the convention of the book, but either way works. And then P minus Px Qz. That's my J. And then lastly, plus, and then we have to cover the K. And so we know it's Px times Qy minus Py times Qx. And that's K. And there you have it. So if you're rusty, that's how you do cross products. Again, and a lot of the problems I'm going to do, I'm just going to start off with these as numbers, and then I'm going to give you an answer. I'm not going to show you this because this is something that I know you know and you can do. If you're a little rusty, again, practice. So one of the things that when you're doing crossing of vectors, it helps is you can essentially draw a line like this, and you know that if I write K, J, I in there, I know that if I'm going clockwise, then clockwise is negative, not positive, it's negative. And so I know that if I write K cross J, that's a negative I. So K cross J equals a negative I. If I do I cross K, that's a negative J, and so forth. If I go the other way, now if I draw a line that does this, then that's positive, that's counterclockwise. So that means if I do I cross J, that's a positive K. Or K cross I, it's positive J. And then of course we know that if you do K cross K, that's 0, I cross I is 0, and J cross J is also 0. So essentially just basic convention for vectors. All right. So let's move on. And so now let's talk about torque and moments in 2D. Now, I'm sure you're familiar with torque and moments. You've talked about them in your physics class, but just recall that a torque is just a tendency of rotation. So if we apply a force to a lever arm, in this case, we have F times this lever arm here, the tendency is to want to rotate. So this rotation would be counterclockwise, so it would be a positive torque. If it's clockwise, it's a negative torque. So remember that. That's always the case, and it lines up with the vector math too. Now, in our course, we know that torque is work. It's a force times a distance. So we usually do, the units on it are either Newton meters or foot pounds, sometimes inch pounds, and we'll never mix units. So we know that in order to get a moment, it's just equal to force times distance. And where the distance we define as the perpendicular distance. So if you try to open the door and you push straight onto the door perpendicular to it, you're going to require less force than if you push at a slight angle. So we can think of torque as a lever arm too. So on the left side, I have these two. I have a fulcrum, and so I have mass 1 and mass 2. And so if we know that R2 is a greater distance, then we know that in order for this to balance the torques, force times distance, so F1 times M1 and F2 times M2, then we know that the force here at 1 has to be greater in order for that to balance. On this wrench, this is showing the effect of the angle. And we can see that if we apply a force F up here, where I'm pointing the mouse, that then the distance that is the actual lever arm distance is going to be this D down here, because that's the perpendicular distance. And so notice that we extended the force because we know its line of action goes on and on and on. So we just extend the force until we can get a perpendicular line, and then we have just F times D. Now, we could also do F sine theta, where if we take F sine theta, that's this force times R. And so either way it works. And this is actually, I would say, fairly straightforward. We'll do a few examples with this, but most of the time we're going to spend in this chapter, we're going to talk about three-dimensional torque. So let's just look at a couple of examples. So I've put these up here as 4 examples of what the torque would be. So if we look at this first one here, we have 50 newtons, and we want to figure out what's the torque about O. So this is a good example of transmissibility of the force, because sometimes you'd be tempted to think that this 2 meters has some influence on the torque. But it doesn't, because whether this is 2 meters or 200 meters, the perpendicular distance of this 50 newtons is still only 0.75, because you can consider that 50 newtons goes all the way back to here. Oops. So if I want the answer, it's 50 newtons times 0.75, and because that torque is a clockwise torque, it's going to be negative. And so there's my answer, negative 37.5. Now on this one here, we have, again, the 40 pounds, but we're only interested in this distance. So that 2 feet doesn't matter, except for the fact that we need to account for what is the distance here in relation to the hypotenuse. So this simple 30, 60, 90 triangle, we can see it's just going to be 2 cosine 30. So if we do that, we have 40 pounds, and the distance is 4 plus the 2 cosine 30. And again, this is a clockwise rotation, gives us negative 229 foot-pounds. Oh, got the answers too quick, sorry. This next one, this is similar, 60 pounds. Again, we only care about the perpendicular distance, so it's going to be 60 times 1 sine 45. There we go. And so 42.4. And then the last one. So the last one, and then this one's positive because it's counterclockwise. This one is also going to be counterclockwise. Notice how you have the 7 kilonewtons. The 2 meter doesn't matter. It could be the same as if you drew the 7 kilonewtons here. So we know that that's 7 applied at 4 minus 1 or 3. And so 21.0 kilonewton meters. So that's the basics of two-dimensional, not too tough. So now, also want to, before we do an example, I want to talk about the moment of a force about a point. Now, it doesn't matter if it's in 2D or 3D, you can still do this same method. And what it says is if you want the moment about a point O, and you know the force value and its I, J, K components, then all you need to do is figure out a vector R from the point of the moment to the force. And that's an important emphasis. It always has to go to the force, never from the force to the point, always to the force. Just think go to the force. And so you figure out that vector, and the R vector can be to any point on the force, which is nice. So I recommend just take a convenient point where the force is well defined, but it really doesn't matter. Any point in the force will work. And you do R cross F using the cross product I showed earlier, and that will give you the moment about the point. And this can be sometimes hard to visualize in 3 dimensions when you have a point and you have a 3-dimensional vector, but you have to kind of take it on faith as it works. Now, this example here is one out of your book. I like this drawing because what it shows is the force F. It shows R, where you could just say R to the point A, or if you were to extend the force all the way back, you could get the perpendicular distance if you wanted to. Either way, it's going to give you the same result. So here's an example. This is just a simple 2D torque example. So here we have a 20-pound force is applied to the control rod AB. And we want to know, if we know that the length AB is 9 inches and the moment of the force about B is 120, then what's that value of alpha? What angle is that such that we get that relationship? So pause the video at this point. I try this problem out, and then we'll come back and we'll solve it. Okay, so let's talk about this problem. So here I have the drawing. We have the 20 pounds, angle alpha with respect to the horizontal. We have our given, we're trying to find alpha. We have our 120 inch-pounds, we're given in the clockwise direction, which makes sense because it's pulling that way. So it's technically a negative, but we've drawn it clockwise, so that's okay. So if I come down to my drawing, this is what I want to do first is I want to think of what would be the perpendicular distance. And so this is more of a trig geometry problem in some sense, because I know that if I were to extend that line and then draw something like that, and now I'm going to draw this line here, okay? So what do those lines represent? This is the extension of that line. So I know that this is 65 degrees, right? Because that angle is the same as that angle, 65, 65. I know that that's straight, that's the perpendicular line. So 65, this has to be 25, right? So if I were to apply the force P here, right, at the perpendicular, then I could just say that the moment about B equals force times distance. But I don't know, I don't want P, I want to know what this value is here. So I'm going to call this value P prime up here, and this is P that I'm looking for right there. And so this is my unknown angle, but I actually kind of can infer what it is because I know this has to be 25 degrees. And so I know that if I were to redraw my triangle here, let me just draw a little bigger. So this didn't quite come out how I wanted it to. I mean, in terms of, but this is actually the 90 degrees right here, if that makes any sense. That's the 90 degrees. This is P, and this would be P cosine theta. And this would be P sine theta. So really what I have in this problem is I have P prime, I have P, I know that's 20 pounds. I know this is 120 inch pounds. So I know that this value here, if I was looking at just this strict vector here, then I can do it this way. I can say cosine theta equals 13.33 over 20. Theta equals 48.2. Theta minus 25 equals alpha. Alpha equals 23.2. Now, how did I get that? How did I get the 13.3? So remember that this P prime here, that is going to be the perpendicular distance. So if I were to say 120 equals P times 9, then P, in this case, this P prime, sorry, equals 13.33. And that would be the perpendicular distance force. So now it's just triangles, and I know it's 23.2. All right. So that one took a little longer than it should have. But another way you could do that problem, if you wanted to, you could actually, no, actually that's probably the best way when I think about it. I would just stick to that. So that's a simple 2D problem, but let's do something a little more, I think, straightforward. So go back. So it's one more thing I just want to say. So when you're drawing this problem, you could see that this, if you draw a force straight out from here, that's going to be that 13.33 I found. And then I just made a triangle and then used trig to find that angle. That's all. And just knowing that the only part of this force that makes a torque is the part that's perpendicular. Because when I made the triangle, I had the perpendicular part and I had the parallel part. The parallel part does nothing. It's like if I were to push down this rod straight down the direction of it, it wouldn't cause any rotation. Now let's look at this one. So now here we have a piston, and we have a force pushing the piston down. And so we have the connecting rod, and then it's connected again. Instead of being connected straight to the crankshaft, it looks like it has another rod. But so what we want to know here is we're given that a 2.5 kilonewton force is directed along AB. That means that it's not straight down, it's actually at the angle AB. So we want to know, what is the moment of the force about C? So what moment is being created by this 2.5 kilonewton force? Now notice that this problem, the previous one, there's no equilibrium. We're not dealing with equilibrium. We're just finding resultants, much like we did before. But we will combine what we learned in chapter 3 and chapter 2 when we get to chapter 4. So let's look at this. So here I have it drawn. Now, I know that I have a 2.4 kilonewton going down that way. Now, one of the things is if you look at the dimensions that are given, the 144, 42, it turns out that if you divide this by 12 and you divide this by, actually, I'm sorry, if you divide this by 6 and you divide this by 6, you end up with a, this ends up being a 724 triangle, 724, 25. So we have a triangle that looks like this. So 7, 24, 25. Because as I said, we use a lot of triple triangles in this class. Now, and actually this triangle down here is a 3, 4, 5 triangle. So we'll get to that. So we have the 2.4 kilonewton force going down here. We want to find what moment is created by that. All right, so two ways we can do it. So first off, let's look at how the force affects this system. We know it comes down here. And so if we were to draw this lower part, this is BC, we know that this force coming in at an angle is actually two parts of a force, isn't it? So if force comes in like this, it's actually one part going this way, one part going that way, which is denoted here. And so this actually, if we have the 2.4, this part of the force coming down by the ratio of the triangle is going to be 24/25 of 2.4. This part here is going to be 7/25 of 2.4. So all I've done is I've taken this 2.4 here and I've broken it up into its respective pieces. So the hypotenuse is 2.4. This part here would be 7/25 of 2.4. This would be 24/25 of 2.4. And that's all. So now I know that what the force is here. Then I know that if I sum moments about point C, I have a perpendicular force here at a distance of 56. And I have this force here at a perpendicular distance of 42. That's legible. So I'm going to go ahead and write that out. MC equals 24/25 times 2.4 kilonewtons. So there's my force. Now that's going down. So it's going down like this. So if you follow this line all the way down to C, like that, it wants to make it go counterclockwise. So it stays positive. So sign conventions are very important in this. And then I'm going to multiply that by 0.042. So that's 42 millimeters. I convert it to meters. You don't have to do that. I'd like to, but you see where that came from. So that's the perpendicular distance. And then plus, because this force here, the 7/25 of 2.4, that's also going to want to rotate counterclockwise about C. So plus, I'm going to write 7/25 times 2.4 kilonewtons, and then times 0.056 meters. So what I end up with is 97.768 plus a 37.632 gives me a total of 134.4. That's going to be in Newton meters. Okay, so I went ahead and converted that. So this was kilonewtons, that was meters. I converted it to Newton meters. All right. So that's that answer. Now, there is another, you could do it. There's one other way you could do it. Actually, two other ways you could do it. But the one way is you could just look, for example, if you go back up to this drawing here, you notice that the force acting on here has this part, right? This downward part, and it has this part here. So if we draw the line all the way down, that actually goes right through C. You can see it better in the picture, but this goes right through that. So if I take my moment about C from A, then the only force that matters up at this point is this 7/25, because the 24/25 value has a distance of 0. So I could also write this as MC equals 7/25 of 2.4 kilonewtons. And that would be multiplied by a distance of 0.2 meters. So that's a total of 200 millimeters from there, 56 plus 144, 200 millimeters. And I get 134.4 Newton meters. Now, the last way we can do this, and this is how you're going to do this when you get to 3 dimensions, because we won't be able to find the perpendicular distance, is if you did R cross F. Because even in 2D, now we know in 2D when we cross products, we know that I cross J is going to give us K because we know the rotation is out of the board. It's either positive or negative. But if we think about that, if we look at our drawing relative from C, and I'm just going to do it for B relative to C, if I go from RB to C, so RB relative to C, what that means is that I'm going from the point of the rotation to the force. So if I do that, that's going to be negative 0.042 meters, right? Because I'm going to the left, negative. And it's going to be a positive 56. So plus 0.056. So that's my I and that's my J component. And then my force is negative 7/25 times 2.4 and minus 24/25 of 2.4. So that's my I, and that's my J. And that's because when we look at the force from this point of view, it's negative and negative, both X and Y. So if I go ahead and I do my cross product, I get negative 0.042 times 24/25. That's going to be a negative times 2.4. So negative times negative is a positive. And then minus 0.056 times a negative 7/25 times 2.4. So negative minus, so it's going to be a positive. So basically it's a positive plus a positive. And these are the same numbers we had up here, so it makes sense we're going to get the same result. So I know I went through that part really quick. We're going to do more of these R cross F because that's really what you're going to have to do in all 3D. So let's talk about 3D now. So we finished that problem. So when we're talking about 3D, remember that we mentioned that if you have point A and you want to create a moment about O, we know that the moment about O is going to be the force, any point on the force, any point in the force and the distance from O to any point in the force. So if you have multiple forces, though, you have to treat them all the same, all differently. And what I mean by that is if you say, for example, point A has 4 different forces on it, then you can either do a R cross F for each force, or because they all emanate from the same point, you can add these forces together to create a resultant and then just do cross F for the result. So in some cases this works where they're both the same. Other cases you'll have forces that are at different points, in which case you'll have to do the additive method, but it works fine. And so this is just a little more work, but the basic principle is still the same. So this is example 5 worksheet. So if you haven't downloaded it, pause the video and go ahead and do so. You'll want to have that one for you when we do this problem. Now, this problem is a 3D moment about a point. We have B, and that's where the 2 tension lines are. And so notice that we're given the scalar value AB, 550 and 660 respectively. But if we're going to do R cross F, we have to convert those to vectors. So just like we were doing in chapter 2, we have to take this scalar value of AB and make it into a force vector. The other thing is we need to figure out what is the R vector, because we're trying to take the moment about the O. And so O is not labeled here, but it's assumed to be the trunk of the tree or the origin. So O is down here. So let's go ahead and work this, try to work this out. So first figure out what tension AB, tension BC are in vectors. Figure out the vector going from O to each of the forces. So you could go from O to A and O to C, or more likely, I would recommend going from O to B since it's a common one. Then you only do one. Do your cross products, add them together, and you have your answer. So take a few minutes, work this one out, and then when you're ready, replay the video, and I'll show you how to solve it. Okay, so you've given it your best shot, you've tried it out. So here is my drawing. So I know that for this, here's everything you've already drawn down, the give and the find. So let's go ahead, our governing equation. And that's going to be moment about O is going to be equal to R, B relative to O, crossed with tension BA plus R, B relative to O, crossed with tension BC. And so, but we can combine. So I would say you can, in this case, because they both have a common point, you can just combine them. And so that works easily enough. So let's go ahead and figure out. So we have BA and BC. So we know that this is just out of chapter 2, this first part. We know that tension BA is going to equal lambda BA. I'm sorry, tension BA scalar times lambda BA. And so we know that lambda BA is just going to equal negative 0.75 in the I minus 7J plus 6K. Take the magnitude of those, we get 9.25. Now I don't usually put units here because they cancel. Lambda is a unitless value. And so if we go ahead and multiply through, we get TBA equal to 550, and then that's going to be multiplied by negative 0.75 I minus 7J plus 6K all over 9.25. All right, so now we have that. So if we go ahead and multiply through, we get a value of negative 44.6 I minus 416J plus 357K. So now we have our tension. So we're going to do the same thing with BC. I don't think I need to show you that. I think you could figure that on your own. So I'm going to just show you BC's answer. And so this is tension BA. So you're going to find BC, from B to C. So I'll give you a hint. If you're going from B to C, it's going to be 4.25 I minus 7J plus 1 in the K. And you're going to divide that by 8.25. So work that out, multiply through by 600. And what you should get for that is 340 I. This is for tension BC. Minus 560 J plus 80 K. So add them together. What do we get? 295 I minus 976 J plus 437 K. So I'm calling this my tension resultant. And that's that. So now I just need to do my cross product. And so I'm going to do that. And I'm going to say the moment about O, in this case, is equal to RB relative to O crossed tension R. And I know that RB relative to O is just what? 0, 7, 0, right? So I didn't put it in IJK. Well, this is IJK, but it's just 7. Or we're going from O to B, so it's positive 7. Never go the opposite way. Always go from the point to the force. So I know that that's the quickest way. Now, I could have done this where I went from O to A and then done TBA crossed with that. I could have done TBC crossed with O to C and added them together, got the same answer. But why do all that extra work? Be efficient. So this is good. 0, 7, 0. So go ahead, plug that in. 0, 7, 0, 295, negative 976, 437, IJK. And this again, if it helps, label this over here. That, and then MO is that. So I go ahead and do my cross product, 0. So for I, 7 times that. So that's 3,059. I, that times that, minus 0. And then when I do my J, there is nothing. And then I do my K, it ends up being 0 minus 7 times 295. So this ends up being minus 2065. So my final answer, is this I can write that as Newton meters, or I could write it as, with the proper sig figs, the best way to do that, because it has 4 and 4, we don't want that, 3.06 I minus 2.07 K, and that's going to be in kilonewton meters. And there you have it. Now, I realize my writing on here is not perfect print. On your homework, I'd expect to be better than this because you have more time to do it. I'm trying to go through the problems quickly, not bore you to tears by taking time. But just remember, if you have to write it legibly so you can read it, and I'm not as big a stickler as some of the faculty you run into down the road. So good habits are good to start now. Okay, so that's that example. Hope you don't have any questions on it, but by all means, chime in at office hours if you do. Now, I have one more example on that worksheet I want to do, and this combines the 3D tension vectors that we did at the end of chapter 2 with moments about a point. So let's look at that problem. And here we go. So we're out fishing. We have our 6-foot fishing pole AB secured into the beach, and we decide we're going to try to catch a megalodon, and never mind, it's been extinct, but that's okay. And so it takes the bait, and we have a force of 6,000 pounds on the line, and you can assume that that's going from B to C. So our tension goes BC. So that's important. It goes that. So we want to determine the moment about the point A by that tension, BC. So you notice that in this one, because we have the two angles, that means that we're going to have to first figure out what is BC in IJK components. So here we have our 30 degrees ends up being our phi, and the 8 degrees ends up being our theta by our past convention. And the 45 degrees is what we're going to use to determine our A relative to B vector. So go ahead, now that you know that, I would first start by finding tension BC in IJK components. So this horizontal line here should give you a hint. That's going to be what you're going to use to find the X and Z component. And then you'll get your Y component from the 8 degrees. And then just figure out what is the vector, our vector, going from A to B, do your cross product, and you're done. So I know I said like it's easy, but after a few of these, you'll find it that way too. So go ahead, take your time, work on this, pause the video, and then when you're ready, come back. Okay, so you figured it out. You're just checking your answer. That's great. Or you're not positive. That's okay too. So here we have our drawing as it was. And we know that the moment about A is going to equal RB relative to A, right? Because we want to go from A to B, always to where the force is. Now we know the force is going like that. So that's going to be crossed with whatever our tension BC is. So once we figure out this vector and that vector, then we just cross them and we're done. So first off, let's figure out what B relative to A is. So RB relative to A. Well, if we're going, we know it's a 6-foot pole, it's at 45 degrees, so we know it's going to be 6 cosine 45 degrees, and that's in the J. And then it's going to be minus 6 sine 45, and that's going to be in the K, because it's going in the negative Z direction, and there's no X component. So that's that. And then let's look at our BC. So now we know that our TY, that's the easy one. So we'll say TBC sub Y. That's going to just be equal to the tension BC times sine of 8 degrees. So if we say 6,000 sine 8 degrees, and note that B is going in a negative Y direction, going from high to low. So that's going to be negative. So that's going to give us that T, B, C, Y equal to negative 835 pounds. So now you have that. So in order to figure out the X and Z, we need to figure out what this line is. So that's going to be our horizontal projection. And so we know that's going to be similar as TH. So we know that T, we'll just call it TH, is going to be equal to 6,000 cosine of 8 degrees. And if we do that, we get a value of 5942. So TH equals 5942 pounds. All right. So coming back up here, you'll notice that now that you have TH, if you look at the triangle, if I draw this like that, and that's my 90 degrees in the corner, so it's hard to see, but so this TH is only going to be the hypotenuse in this case. So that means that cosine 30 in the negative direction of TH is going to be my Z, and sine 30 in the positive X is going to be my X. So let's go ahead and figure that out. So we know that T BCX is going to equal to TH, and that's going to be sine 30 degrees, or 5942 times a half. And that's going to be, I'm doing the double negative or equal sign, just to save space. Don't do it when you do it. So 2971 pounds. And then when I get to here, I know that TZ is TH, it's negative cosine 30. So I have 5942 negative times square root of 3 over 2, which is cosine. And that gives me a negative 5146. So my final answer, my final tension BC is 2971 I minus 835 J minus 5146 K. So that's my final vector. All right, so you can rewind and look at how I got that, but it's pretty straightforward. Just taking, you find TH, this is 8 degrees, so you find TH from that, and you find the Y is just the opposite side here, and then you use that 30 degrees to find your negative Z and your positive X. And we already have RB relative to A, so now it's just a matter of doing the cross product. So when we do the cross product, we set it up, moment about A, R, B relative to A, tension BC, I, J, K, and then put in, 0, 6 root 2 over 2, and negative 6 root 2 over 2. And that's just cosine and sine 45 respectively. And then we have our 2971, negative 835, and negative 5146. So there we have our values. So if we go ahead, do our cross product, I'm not going to show you that, you know how to do it. We're going to get a negative 25.4 I minus 1260 J minus 1260 K, and the units are going to be kip feet, where kip is 1,000 pounds. So that's our answer. That's MA. Okay, moment about A by our Megalodon is that. All right. So that's those two examples. I hope they make sense. This should help you with the homework. As far as moments about a point, that's it. Whenever you take a moment about a point, you just find the respective vectors and do your cross product, and you're done. That's all. Now I know that's not super exciting at this point, but again, we're finding the building blocks, or we're building the structure that we need to go on and solve more interesting problems. So bear with me; it'll become more relevant as we work ahead. All right, and I think that's it. Yes, it is. So thank you for listening. This was lecture 5. So stay tuned. Lecture 6 is next. And lecture 6, we'll talk about what do we do when we want to do a moment of force about an axis. How do we do that? So it's going to be slightly different, but still very doable. So stay tuned for that. Thank you.